Thanks for coming here at this time of the day, and thanks to Swati and to the other organizers of the ERC for actually putting this together. I'm not sure with what frequency you guys meet, but it will also be useful for the other faculty to interact with you more closely if you were to come in larger numbers and more interestedly for such meetings. But yeah, here we are. So the goal of today's discussion, so to speak, is to basically get you acquainted with some of the things that I like to think about and I like to work on. So the title, I've kept it fairly evocatively as Techniques for Practical Private Data Analysis and Reliable Storage. It's really a mishmash of 2 or 3 different things. And for the next 45 minutes or so, it's just going to be a tour de force into the kinds of things that I have done in the past and whatever it is that I intend doing here at IBM. So, as some of you may know, I've just been here for about 7-8 months. So, this is my plan as I see it. Okay, so when we talk about data analysis / transmission / storage, typically this is the pipeline that one deals with. So firstly you mine data from some place, then you wish to either transmit it or communicate it from one place to another, which necessitates the design of low complexity schemes for reliable data transfer. I'll tell you what that means. Now, it's one thing to get data from one place to another, it's a completely different thing to store it for long. That is archival storage. It's a completely different ballgame. But the desired data are similar. So just like in the first case you wanted fast algorithms for reliable data transfer, here you want fast ways of decoding the data that has actually been stored. So that is the desired data in the second kind of research area. And the third research area is when you have transmitted data, you have stored it. Now we need to do something with it, which inspires the basic task of data analysis defined very broadly, and particularly private data analysis in this day and age. So the picture that you see here is that of an advertisement for the DPDP Act. This is something that I keep talking about regularly, in the sense that this is an act that's going to come into enforcement the next year. So 2027 is going to see the implementation of this act in practice, which means that every company that mines data from you is necessitated to comply with privacy rules. Right? So there will be an overwhelming requirement for privacy engineers, for privacy data scientists, for private data scientists, and so on. And part of the research that I do is geared towards this task of designing private algorithms for data analysis. So I asked Rob to actually come up with an image that encompasses all these things together, and I took 3 prompts, but I think the image is fairly okay. It's not that much. So there's data transmission, data storage, data safety, and privacy, and apparently it all intersects in information theory, probability, and control. This is something that he told me, and I tend to believe it. Okay. So the focus areas of this lab that I'm trying to build here are threefold, which basically draw upon the 3 research areas that you saw in this. So the first is, in reverse order, practical private inference and learning. So you have large data sets that have already been mined by governments or by big tech firms, and now you need to do data analysis, statistical inference, machine learning on these data sets, and you need to do it practically. So that is the ask. The second thing that I wish to focus on is basically the foundations of modern media, modern storage media. Particularly, there's this line of work on storage on DNA strands, which is actually has been in proof of concept stage for about 10-12 years right now. And I anticipate that it will remain in proof of concept stage for a little longer before it actually sees rollout. But this is an interesting archival storage medium, in the sense that this is storage that is meant for the long term. So suppose I have some piece of information that I want to not read too frequently, that I want to have in cold storage, then this is the potential option for cold storage, archival storage. And the final research direction is more classical foundational work, neither information theory or control coding, quantum information theory and quantum interaction. But what is the research thing that kind of ties everything together? Well, it can be succinctly summarized in the following phrase, which is the design of low complexity practical algorithms that are backed by some rigorous analysis. So this is the maxim by which I wish to live by, and I want my lab to also. So all the work that we do or that we envision to do is going to be inspired from practical considerations, but it is going to be backed by rigorous mathematical analysis. So that is the goal of the experiment. And this is a very non-exhaustive list of collaborators. As you can anticipate, list of collaborators keeps increasing as you gain experience in any field. So the people you see right on top are the people I collaborate most frequently with or have collaborated most frequently with in the past, and a little less so down south. And of course, there are a lot of colleagues of mine at IIT Madras whose interactions I greatly benefit from. So as you can see, these collaborators are fairly fast spread out, both in terms of demographics and in terms of research interests. So there are computer scientists, theoretical computer scientists like those at CMI. There's also my collaborator Prof at Stanford. He also qualifies as a theoretical computer scientist. Then there are information theorists, primarily my advisor at IISc, Arvind, and a close collaborator of mine at the Technion Institute. His name is Neil. And then there are coding theorists, people like Antonia who work at TU Munich, Jonathan who works at Newcastle, Lalita, and so on. And as far as my research on privacy goes, it was conducted in an industrial laboratory. So I have put up my manager in charge there, who was fairly actively involved in my research also. But of course, my colleagues at IIT Madras are far more involved in privacy, and that is one more set of people that I work with. People in both in electrical and DC. Okay, so this is going to be a blow-by-blow account of things that I have been involved in each of these three areas, starting with private inference and learning. And the slide of this presentation is going to be as follows. I'm going to flash at you this kind of a title slide for each of these research directions and try to give you the main buzz phrases or keywords that encapsulate much of my research. So here it is privacy preserving algorithm design and worst case error analysis. So there is some element of doing things in the worst case here to account for extremal distributions also. You'll see what that is. So what is this entire goal of privacy all about? Well, privacy is important only insofar as it informs practical design. So where does practice come in? So it is now very well established that you have a sensitive data set. So for example, I go to a hospital and I volunteer my personal information regarding my current residence address, my age, and also potentially the disease that I am suffering from, which has been reduced to layman's. So hospitals store all of these medical records, and oftentimes they release them for analysis. So how do they release them? They don't directly release these data sets, obviously. They try to de-anonymize these data. They try to anonymize these data sets. That is, they drop my identifiers and so on. Like my name is dropped and replaced with some unique identifier. But as it happens, if you were to do even simple data analysis tasks of these anonymized data sets, you can potentially identify the individual participating in this data set with extremely high accuracy. So this is something that has been shown for even simple statistics like releasing the sample mean or releasing counts. So these are what are called aggregate statistics. I release these aggregate values, but even with these aggregates, I can find out who it is that is participating in these data sets with fairly high accuracy. So the entire goal of differential privacy, as was introduced in the mid-2000s, was the design of algorithms that are kind of resilient to such attacks. So even if I release aggregate statistics, I should not be able to find out exact information as to who participated in these data sets. That is the reason. So what am I interested in? I am basically interested in kind of end-to-end system design for private data analysis. So this end-to-end thing is called a DB pipeline nowadays in the industry. So you start by mining data, then you do something to make it private, and then you do data analysis on that. So that is the typical pipeline at a high level. And these data sets are real-world data sets that come from healthcare applications, from traffic data sets, agricultural data sets, and so on. So these are actual Indian data sets that I've worked on in the past, on which we do these private data analysis. Okay, so it's whatever 6:27 in the evening, and showing you math at this time of the day is possibly vulgar. So, but I'm going to do it. Okay, at some level, I'm going to flash at you some math, mainly to get you on the same page as me regarding the high-level picture of these things. So, what is differential privacy all about? So, at a high level, what it's trying to do is it's trying to protect one single individual from de-anonymization. So essentially, if I release a statistic, I should not be able to find any one particular individual that I'm interested in with high index. So in particular, consider two different data sets. So this data set D1, data set D2. What do these data sets have? They have the identities of the users and they have the samples. So any data set at the end of the day is just this. And what is the difference between these two data sets? The only difference is that one of these data sets has me. I participate in D1, but I don't participate in D2. That's the only difference. So what I want a private algorithm to satisfy essentially is that the output of the algorithm on the first data set should not be too different from the output of the algorithm on the second data set. So what that means is the algorithm's outputs don't really depend on whether or not I participated in it. So this mathy looking equation that you see there is just saying so much. So the probability that this algorithm returns some answer y is not too far away from the probability that the same algorithm on the second data set returns the same value. So how far away is determined by the z to the epsilon input. So what is all this e to the epsilon? Really think of it as 1 plus minus. Alright, so this is what differential privacy is. This is the definition, and all that people have been doing in the past 15 years or so is to design algorithms that respect this notion of privacy. So the output of the algorithm must respect this definition. And that is this sequence of papers that you have seen. These have won like paper awards, they have inspired work in the industry, they have like lakhs of citations and whatnot. And this field is continuing to grow. Even right now, if you check any preprint server like archive, you will see multiple papers on differential privacy. Cool. So, how does one go about actually doing this in practice? Well, I'm going to give you a simple example here just to get you guys acquainted with how you do this. So, suppose you have data from a particular city, and typically this is spatio-temporal data. Okay, so, this is data that you mine from different neighborhoods. For example, you have air quality indices from Kasturba Nagar, you have air quality indices from Keke Nagar, from Vesmapuram, and so on. Or say for example, you have even more sensitive information. Like I go and shop in 3 different shops in these 3 neighborhoods, and you have details of my credit card spends in each of these 3 shops. So this information, predictably, I don't want it to reveal much about it. So the end goal is to, you can just ignore the stuff on traffic here, that's just an example. The end goal basically is to privately release statistics from these different neighborhoods with low reconstruction error. So what does that mean? So I want to release statistics about credit card spends in each of these neighborhoods. So there is a particular chain of supermarkets in each of these locations, and they mine data from the people who come and shop there. So they have data about credit card spends as against the credit card numbers of people who spend. But I want to say, find out just the mean, or I want to find out the number of people who spend more than 3,000 rupees on one particular day in each of these three places. But I want to do this privately, okay, in some sense. So the private algorithm that I designed for each of these three supermarkets, it must predictably satisfy the first equation that you saw previously. So that is the equation, that is the gold standard that requires that I require for this algorithm to be called differentially private. But privacy alone is useless. Right? I should be able to do something with the data that you're getting. So this is what we call as reconstruction guarantees. So I want to be able to reconstruct the statistic that I'm chasing after, which is the number of people who spend more than 3,000 bucks at each of these three places, while not revealing information about any particular individual in these three data sets. So that is the name. Okay. So I do have slides that go into detail about the work that I was involved in, but I'm just going to give you a high level overview. So the overview is, well, we have designed algorithms for the specific release of certain statistics across these different neighborhoods in such a manner as to also allow for low reconstruction. So these papers, what they do is they try to pre-process the data set in a certain way, so that if I design a differentially private algorithm on top of this pre-processed data, it is going to have low reconstruction. So we don't actually toy with the algorithm, the private algorithm per se. We only toy with the pre-processing procedures. The reason being, there are fairly standard algorithms for differential privacy that also have near optimal errors if the data set that they work on is regular. So the question is, you want to make these data sets fairly regular. And how you go about doing that is the subject of all of these papers. These papers have been published in both Indian and international conferences. Some of them are eventually going to find their way into top journals, and some of them have even received awards. So this was one direction. The other direction was, I don't want to release particular statistics of the data. I want to release a kind of a meta statistic from which I can derive other statistics. So I don't want to do particular pre-processing strategies for particular statistics like mean, variance, and so on. I want to just release one representation of the data set itself, from which I can derive other statistics privately as and when I want. And the statistic that I'm chasing after is the CDF, cumulative distribution function. Okay, as you will know, suppose I release the CDF, I can always derive from the CDF, say, any moment. The first moment, that is the mean, second moment, variance, and so on. Also things like the mode and so on. So this was the goal of another work that we did at my previous organization, where we designed private algorithms for CDF release, for meta statistic release. And an additional design item in that procedure was that whatever I release must also be consistent. So this was a question that came up in the US 2020 census also. So the question was, suppose I release histograms or CDFs of data. I also want the private version of these statistics to obey the same standard properties of the non-private statistics. So for example, histograms are non-negative, CDFs are monotonically non-decreasing. I want the private versions of these to also respect the same properties, because I can use those versions then for downstream post-processing. So this was something that we optimally did for CDFs for a fairly general class of mechanisms in our previous work, and this is under review with the information theory transactions. Another very recent work that was actually got a best paper award at the IKDD Records is a work that is completely different from differential privacy. So this is more heuristic in the sense that it goes back to the very foundations of what privacy is. So again, returning to this example, right? So you have three franchisees of the same supermarket. or you have 3 different hospitals in the same hospital network. So there's a big hospital chain, and they have these small hospitals in different neighborhoods. And I go to hospital 1 in order to check on my health, and the doctor says something, but I don't believe him entirely. So I go for a second opinion in a different hospital. That's what people do usually. But I have a nosy neighbor. Okay? I have an adversary who somehow gets information about the patients who visited these different hospital franchises. Again, remember that these releases are individually anonymous. Okay. So individually, each of these hospitals has said, "Ah, great, I've done a great job of anonymizing everybody that has come to me, and this is the list of people that came to me. I've dropped their user identifiers, I've grouped them so that you can't make out who came to me in particular, and so on." But the task is, okay, if I put even 2 of these records together, if I join even 2 of these databases together, I can actually reliably find out who visited both of these hospitals, and hence find out the sensitive attribute, that is the disease that is happening. So this is something that we formally or mathematically showed in this work. This was the classical database join problem. So this is something that database researchers are very concerned about. And we actually formalized this problem mathematically and derived its worst case problems. And there was something more that we did. We basically designed algorithms to alleviate this problem. So we said this is a bad thing. So let us design notions of anonymity that don't have this kind of bad behavior, and let us design algorithms for meeting this new notion of anonymity. So you can find more details about these works when you read the full versions or even the abstracts of these papers. I'm not going to go into the details here. The goal is just to give you a high level. Okay, so that is as far as what I have done is concerned. What is it that interests me now? Well, the extensions of whatever differential private algorithms that have been designed in the past 5 years certainly do interest me. But there are also other questions that are out in the open that I think require addressing. The first of these has to do with, all of these have to do with the broad topic of AI safety or AI alignment. And they go as follows. So the first question that I particularly like is the question of watermarking language model outputs. The goal is somewhat like this. I have students in a course, they all cheat in exams, and I'm super pissed off with them. I want to know whether I am falsely accusing them or rightfully accusing them. Because I have this gut feeling, when I look at an assignment, I see 2 people have written essentially the same thing without discussing with each other, then I know it's copied from a different source. But then I'd be falsely accusing them if I, just went out and yelled at them. So that is not something that I'd like to do. So there should be some way for me to find out whether outputs have been generated by an LLM or not, reliable. So this is the entire question of LLM watermarking. So this is particularly for text language, for text large models, not for image models. So how do you essentially insert some kind of signal in the outputs of an LLM while not damaging its quality in some way? So you guys want to, for example, turn in reliable and good answers to me, right? So you want the LLM output to have good quality. At the same time, well, I want to distinguish the LLM output from outputs that have been generated by humans. So this example is fairly adversarial, it's you versus me. But in practice, this has far greater consequences than all this. For example, I don't want fake news to go out in the open. I don't want to do a post hoc kind of identification. Fake news has gone out, this news is fake. That's not what I want to do. I want to prevent it at this stage of this region. This is the entire question of LLM watermarking. Then there's the question of AI alignment defined broadly. So this is the following question. I have a very excellently fine-tuned language model. Okay. Fantastic outputs, but it's like super rude to me all the time. It's swearing at me. It is, providing outputs that are potentially harmful. It's pushing me towards things that I self-harm and things like that. Or it is, also providing fake information and so on. So the goal here is to actually produce, again, AI model outputs, language model outputs that are aligned. the sense that they are aligned with human preferences. So you have a reward model that you must train, and you want these language models to be aligned with respect to that reward. That's the broad goal of AI. It has intersections with reinforcement. And the next question that I'm interested in is private inference. This ties back to everything that I've spoken about, particularly in the context of clustering class. So I want to identify, say, home or office locations in a city while not being too partisan in the way that I go about this process. So I don't want this to bias me against certain communities. Right. Okay. So that's the end of the first research direction. So I'm going to talk about the remaining two in turn. And this is going to be a completely different direction based on your interest and based on my interest. Also, we can work out things with your interests. So this is on DNA-based data storage, particularly the foundations thereof. So this is a fairly new way of thinking about data storage. Mainly that you can synthesize DNA strands artificially in the laboratory that can store information with extremely high information density. Okay. So for example, if you're just doing it on standard magneto-optical storage, if you look at a real cluster nowadays, they are not SSDs. Okay. So you will not find solid-state drives in these clusters because solid-state drives are not very reliable and they are also very expensive. So what you see in these large clusters are primarily slightly older technology, magneto-optical technology, hard drives, flash drives. But yeah, even these have their problems, right? So the goal of this DNA-based data storage is to come up with archival technology that can survive for very long, on its own without failing. But under the assumption that I'm not going to query this media too often. Okay, so this is cold storage, like what I said. So there are guarantees for this. For example, people have estimated that the longevity of data that's stored on DNA strands is roughly 1 million years. How have they done this? I mean, we are not 1 million years old. It's basically by finding out how the proteins in DNA denature upon heat. Okay, so heat is a fairly reliable indicator of how aging works, particularly with DNA strands. So this is a simulation that has been done in laboratories, and this is an estimator. So how do you go about actually realizing this in practice? There are labs that do this. So the basic idea is, okay, I have like the Constitution of India written up in my computer, and I want to store this on a DNA strand. I just synthesize strands just the same way that you would think. So you have nucleotides on DNA strands. ATCG are the standard nucleotides. Nucleotides put together form an amino acid sequence, and they in turn generate proteins. So that is how these things happen inside the human body. So if you want to generate a DNA strand, you basically want to encode information onto these nucleotides. So you want to generate these nucleotides in a certain way, and that generates the strand. Strands are typically complementary, so you generate just one strand, and the other strand is just complementary base pairs. So A pairs with E, so A pairs with T and C pairs with G. So these are, I guess, hydrogen. Right, so we have stored data. So storing is just encoding and then putting it in your refrigerator, in your freezer. But how do you read from this? The way in which you read from this is slightly more complicated. Typically, when you store DNA strands, you store them in an unordered fashion. Okay, so these strands get all mixed up. Right? You store them in a fluid, and so typically they get all mixed up. So you want to extract information, ordered information, from this unordered fluid. So the way you do this is first you do what is called PCR amplification. So this is something that you would have heard of during your COVID times. Polymerase chain reaction is basically to amplify signal from noise in a certain sample. So you run a PCR amplifier, and that generates several copies of the DNA strands that are present in this. is the basic idea. Then you sample the strands from this fluid at random and you do. So this is high level, this is what happens. So whatever we have is basically foundational understanding of how this process goes. So you can model the entire thing like a communication setting. So you have storage, you have unordered strands being stored, then you have sampling uniformly at random, and then you have the reading process. And the final goal is to try to find out how much information can you store reliably on this system. So my collaborator and I have quite a few results in this aspect, particularly about how many strands should you sample in order to reliably recover a certain piece of information. Okay? So this is really again information theoretic work, but it appears in the biological context. So again, this is joint work with groups in Europe, and it's primarily these European guys who are involved in this DNA sequencing. So that is the story until roughly a few years ago. But right now there's a big breakthrough in DNA-based storage. It's called the third wave of DNA sequencing. It's called the nanopore wave. So instead of sequencing DNA strands using what is called shotgun sequencing, people have come up with a new technology. This is called the DNA nanopore. That is a different way of reading DNA strands. I don't want to get into how the nanopore works, but take it from me that this technology is more reliable and that it can read really, really long strands of DNA. So the question is a repeat question. Okay? So for this new system, for this new nanopore based sequencing system, what are the fundamental limits of storage and reliability? So this is again a very recent work with my collaborator. It appeared in the Selected Areas of Information Theory journal and has also come out in Prof. Okay, so in this slide, what are questions that interest me? Well, one thing is, of course, the capacity or the fundamental limits of DNA storage systems. A closely related problem is what is called trace reconstruction. Okay, so basically, you have multiple noisy observations, like multiple noisy strands that you see, and you want to reliably recover one single strand. So all of these noisy strands essentially come from one given strand. So they are all independent noisy observations of the same thing. So you want to reconstruct one single guide from what are called traces. So these different strands are called traces. So this falls squarely in the realm of statistical learning. So this is something that the guys at IIT Madras are very enthused by, I've heard. So this is work that really tries to find the trace complexity or the sequence reconstruction complexity for different trace reconstruction problems. And in general, any other mathematical problem in computational biology is again something I'm interested in, particularly things related to sequence alignment, composite DNA sequencing, and so on. So you can talk to me in detail about these things later if you're interested. Okay, for the final research area, which is on classical and quantum information theory encoding, I am basically interested in some of these really big open questions that still remain. So classical information theory encoding is fairly mature, but there are still really simple but big open questions that remain unanswered. And these questions to me take the following two forms. Firstly, can we derive fast algorithms for decoding good codes over standard channels? So you have seen in your usual information theory course or whatever that you can always design random codes that do really well over memoryless channels. So if you have a standard Shannon memoryless channel, you can always have a random coding scheme that does very well. But the goal is you can't go to a Qualcomm and say, okay, here I have a random coding scheme that does well. They want a code. They really want, say, a generated matrix, and they want a decode. So this is something that I preach and evangelize about in my ECC course. The fact is that the encoding process is remarkably simple. The decoding process is what is remarkably complex. And to this day, we don't have a clear idea about how to do optimal decoding for codes that actually do it. So we do have proofs that this particular code, for say a polar code, okay, forget the polar code family. Say for example a read Muller code does really well over memory channels, we have proofs. But what are these proofs based on? They are based on decoders that do some very computationally expensive tasks. They do like maximum likelihood decoding, map decoding, optimal decoding tasks. These are not low complexity decoders. So we actually want to design algorithmically good decoders for these really good codes. So that is a really broad question that interests much of the information theory community and interests me also. The second goal is, can we design near exact algorithms for fundamental counting problems in coding? So if you've taken a course in error control coding, you'll know that the basic question 101 has been unanswered. This is the question of how can I maximize the rate of a code while also maximizing its error correcting capability? How can I maximize the rate of a code while maximizing the distance? So this is the correct rate distance trade-off is still unknown. Right? This is despite close to 75 years of work on coding, we still don't know what the actual rate distance trade-off is. So the question is, okay, if we don't know the actual rate distance trade-off and still cool, can we get approximate ways of computing this rate distance trade-off? And much of my work in the past has been centered around these two things. One is about deriving state-of-the-art upper bounds for the sizes of constraint codes. This is what comes exactly to student paper a lot. And it kind of related this problem to a theoretical computer science problem of computing Boolean Fourier coefficients on the Boolean level. And another question that I worked on was basically a fundamental counting problem. So basically, I want to find the weight enumerators, so to speak. Okay. You guys may not know what the weight enumerators are, but it's okay. Take it from me that finding weight enumerators for well-studied families of codes is not an easy problem. So my goal here was to design approximation algorithms in the sense of the theory computer scientists do for this problem of computing weight enumerators. And this is what we did. We had a polynomial time approximation algorithm in last work, which actually gives you good guarantees also in practice. This was based on MCMC, Markov chain Monte Carlo. And it also helped us really understand weight distributions for codes that were relatively unstudied in the past. These were completely new state-of-the-art results. And in very, very recent work, I have to address my other question. Given analysis for a fast decoder for the read Muller family. So read Muller codes perform really well on memory channels, but I want a fast decoder and I want to say good things about fast decoders. So this work was essentially about deriving guarantees for these fast decoders for certain code families. This is again a work that I personally would consider really pushing the state-of-the-art. Okay. So that's as far as what I have done in this research direction. What is it that interests me now? Again, I have not answered my first question fully. So I am still interested in the design of fast decoders. Especially, this is an area where really creative solutions can arise, particularly from minds that have not been bothered with this problem for too long. So if you approach this problem from a fresh angle, it's very likely that you are going to see things that an experienced person may not see. So fast or low complexity decoders, at least that work heuristically, is something that interests me. So if you have a fast algorithm and you can show good performance, then that is something that will catch my eye. The second thing is fast decoders for quantum counterparts. So we have these so-called quantum LDPC codes, QLDPC codes. There's been a real breakthrough in quantum error correction with these QLDPC codes, but again, the question remains of how to do decoding for these codes. We know the codes do well, but how do you decode these codes? Or for that matter, topological codes, story codes, service codes. Okay, so this is like a absolutely fast tour de force into the things that have been done and the things that interest me now. But since this is an audience of primarily undergrads and a few grad students, the goal is to basically also convey to you how you can possibly interact with me if it interests you on topics such as these. So for the undergrads, this is my recommendation. It may look fairly outdated and fairly repetitive, but this is a time-tested kind of pathway. The first way is to just build your foundations. Okay, so don't try to delve into research as soon as you step foot into IT class. Build your foundations in probability, error control coding, information theory, linear algebra, so on. But once you have built your foundations fair enough, so you need to score well in these courses. Your grades do matter. You can come and talk to either me or to faculty who interest you about these particular topics. The goal is to initially settle on a research problem that matches your aptitude and my interests. Okay? So this is something that we can work on in the initial stages of your life here at IIT. And then we can get on to specializing via electives. Okay, so take electives that I or other faculty offer, and I'd like you to do well in them. Just sitting in the course is not enough. Then we get to the actual research part of it, where you actually present papers from time to time. We have weekly discussions, and then you start collecting results either by our code or by our doing theory, that is math, and by our regular technical journal. Okay. So one understated part of doing research is the writing. So there are people who are very good at doing math or writing code and so on, but completely skip out on this path of journaling whatever they have done. So it is very likely that 3 months down the line you have no clear idea of what has been achieved in the last 3 months. Results are all over the place and we get nowhere with our research. So we don't want that to happen. And so I strongly suggest that if you are a student who is interested in research, particularly at the early stage of your career, get into the practice of writing up whatever you have found, even if it is small steps. And the recommendation is that you stay on any particular problem that you pick for long enough. Don't fly from one problem to the next because one seems more glamorous than the other. Just stick on one problem for long enough and the results will start showing systematically. So the expected outcomes that you can expect from work with any faculty in theory, and in particular with me also, is one, you can build a code base for many of these works that I'm interested in. For example, you can build a code base regarding heuristic decoders for specific code families. So that is a contribution of interest broadly. You can also start by writing short posters in workshops and so on. There are several Indian workshops that you can attend and publicize your work in and reach the community at large. The JTG is one such workshop. And this will actually set the stage for you to actually start writing conference papers, research papers and so on in your third and fourth year, potentially in your fifth year. So one thing that you will benefit at the end of it is, of course, networking with peers from outside India or globally recognized people within India. So this will really broaden your network. Okay, so I typically have a few openings for research projects at large with both master's students, so MTech projects are available, and there are a few BTech and DTP projects that are also open, UGRC via projects. But before you apply, come and talk to me about the things that you are interested in, and I'll tell you what is it that I envision in our things going forward. That's the only way things are going to work. And of course, if you ask me, longer project durations are going to be favored over shorter ones. So I'd much rather have a guy who's going to stick around for about a year or slightly longer, and someone who's going to fly away for 4 to 6 months. So this is all that I had to say. Thanks for being here.